Hey guys, in this video we continue talking about Taylor series method. I think you have remember we use Taylor series to find numerical solution to this kind of initial value problem, right? This is the initial value, this is your first order differential equation, and we found an approximation to this function, right, using Taylor polynomial, right? So that means we consider full Taylor expansion. So this is it is a which is a infinite series, right? It's an infinite series. If you cut down your infinite series from somewhere, or if you ignore the rest of term from somewhere, right? So you get a Taylor polynomial, right? So now you can use that Taylor polynomial to approximate, to get to find an approximation to this, right? We did in my previous video, so this is the error. So if you use this Taylor polynomial, mth order Taylor polynomial, so you get this much error. This is the exact, this is the approximation one, right? I hope so. So when you consider only first two terms like this and cut down, you get rid of these all other infinite terms, right? Then we call it is Taylor no forward Euler step, and you can consider three terms of your Taylor expansion, right? So you can find you can, yep, this is an approximation to, so this is an approximation to, this is an approximation to x evaluated at t naught plus h, right? Or t1, x of t1, right? So likewise we started discussing these things. So in this video we are going to talk about a couple of examples regarding this. Yep, our first example, set up Taylor series method with m equal to 1 and m equal to 2 for this initial value problem. This is your initial value, this is your first order differential equation, right? So one can find that one can verify that this is the exact solution to this system, right? Why I'm saying system? So here you consider the differential equation with the initial condition. This is called initial value problem. So you can verify this one, this exact solution. This is a solution to this system by subbing this one into here, right? You can substitute this, you can verify that, right? Both condition satisfies, right? Both conditions satisfied, right? All right, so this is your initial condition. At t0, first step would be, let's find the numerical solution using Taylor series method, right? First consider m equal 1 case. That means you just consider first two terms of your Taylor expansion, right? So which is this, so yep, so this is the general form, general. So if you know, yep, so this is an approximation to, if you know this one, approximation to x of t k, right? So the when m equals 1, right, you can define this by considering first two terms of the Taylor expansion, hf of tk comma xk. So f is equal to f of t comma, this is your f of t comma x, right? So the Taylor, so this one, this iterative equation, right? Xk plus 1 is equal to xk plus h, and the function f evaluated at these 2 points. Just by subbing these 2 points into here, you get this, right? So this is your first order Taylor series approximation. So this is your, so xk k plus 1, which is this, or you can simplify this, yep, which is this. This one is this is an approximation of x of t k plus 1, right? This is an approximation. So this is called the first order Taylor series approximation or method, right? So let's talk about Euler's method. Yep, Euler. What do you call? Yep, Euler. Yep, forward Euler method, right? All right. Now let's consider m when m equals 2. Now you consider only first 2 terms of the equation. Okay? So m equals to, yep, 1 2 3, first 3 terms of the equation, right? Okay, so that means if you have general xk, right? So suppose you found this iterative, so how do you find the next iterative? So we just consider the first 3 terms of the, yep, xk plus h x prime at, yep, at k plus h squared over 2 factorial 2 xk double prime, right? So xk prime is this one minus xk plus e to the minus tk, which is this, plus, yep, 0.5 h squared and x double prime, xk double prime. So you can find that, yep, x prime is this, so differentiate this one with respect to t, right? So when you differentiate this with respect to t, so this becomes negative x prime, and this becomes negative e to the, yep, t. So x prime would be this, you can sub this value into here, then negative, yep, negative positive, and positive e to the k becomes negative e to the k, because you have negative here and negative. Then this is your x double prime, and x double prime, yeah, xk double prime is xk minus 2 times e to the minus kt. Yeah, sub that one as well. Right, simplify this. So this is the approximation. This is an approximation to, yep, to this function, x evaluated at t k plus 1. So this is called, yep, second order Taylor series approximation, right? Second order Taylor series approximation. Similarly, you can find the third order when m is equal to 3, third order. Then you have to find the x triple prime, right? Fourth order, fifth order, and so on, right? If you have time, right? So here, look at this graph. So I plot the solution curve. So solution, exact solution is this: t to t times e to the minus t. So yep, the blue solid line represents the exact solution x of t, right? Yes, let me zoom this one. Yep, this blue solid line represents the exact solution, and these red cycles, the graph of this graph with red cycles, represents the curve when the first order Taylor method. These are the solutions. These red circles. Yeah, this curve with red circles represents the first order Taylor method. That means first order. Using first order or Euler method, using the Euler's method, this one, you get this the curve with red circles, right? And the other one, and the crosses, the graph with crosses represents the second order case. You can see that the second order Taylor method, so the solutions with the solution of second order Taylor method lies on the exact, yeah, that one tally with that one tallies with that one is tally with the exact solution, not like the first order method. You can say that the second order method is much, the approximation, second order Taylor series approximation is much better than the first order one. So this is the first order approximations, Taylor series approximations. This is the second crosses represent the second order Taylor approximations. All right. If you look at another example, set up Taylor series method with first, second, third, and fourth. Right. So this is your differential equation. This is the initial value problem. So one can verify that this one is the exact solution to this system, right? So how do you start? How do you start this problem? First, you have to discretize the timeline or independent variable. Start of it t0 here is 0. Yep, this is your t0. And the next iterative t1, t2. Suppose we found up to t, and tk, we know xk, right? These gaps are equal to h, right? So suppose right, so you know that this is your f of t comma x is this one, f of t comma x. Remember, t is the independent variable, x depends on t, right? X is the dependent variable. Here t is the independent variable. Don't get confused, right? All right, so f is this one. Right. So then what is your x prime? So for this question, x is equal to e to the t, right? So when you differentiate exponential function many times, you get itself. That's why you get x double prime is also equal to x prime is also equal to x triple prime. Anything you differentiate any times, when you differentiate x many times, you get itself. You get exponential function, right? So x, the mth derivative of x is equal to x. Then you can set up the mth order Taylor mth order Taylor expansion. So this is, so that means you consider only m plus 1 terms of your Taylor polynomial, Taylor expansion. Right, first term, second term, third term, and mth term. You know that this one is same with x, then x, yep, this is h. So yep, h time xk. So this one is your xk prime, this one is xk double prime. Yep, this one is your xk mth, yep, mth derivative of xk, right? All are the same because you get xk here, right? X. Right, so when m is equal to 1, you get these two terms, which is this. When m is equal to 2, that means you consider only first three terms of your Taylor expansion, which is this. Get this. For this one, yep, and these are the results. Yep, the solid red line represents yep, let me, yep, yeah, solid red line represents the exact solution, and the curve with circles, yep, represents the solution approximation of first order one, and the other one, yep, and dot. So those graphs, all other orders, all graphs, all higher order representation align with this solid exact solution. You can see that when you increase the order of your Taylor method, you can get accurate solutions. So not like first order Taylor method. So this curve with circle gives you the first order Taylor method approximation. Yep, approximations. So yep. All right. So except the first order method, all the other order approximation approximations are very close to the exact solution, right? You can notice that, right? I hope you understand this one. So how do you find this equation, this approximation, right? So when you are given a problem, when you are given an initial value problem, how do you compute the first order? Yep, how do you compute this approximation? This is the first order. Yep, first order approximation. Taylor series. Yeah, second order Taylor series approximations. Yep, and third order, and how, and you can do on your own, right? So you can find solutions like this. So you can see that. So yep, second, yep, this is except. So this is the first order Taylor approximation, and this one is the second order process represent second order approximation, Taylor approximation. So you can see that second order approximations are close to the exact solution, not like first order approximations. So from this example, so you can see that so these are curved. Yep, these cycles represent, these circles represent first order approximations, right? So you can see that all the other except first order approximations, all other higher order approximations are very close to the exact solution, right? All right, so in my next video I will talk about error analysis of Taylor expansion, expansion method. So I hope you could get a better idea about Taylor series method, right?